that came up in last lecture when I did this qubit swap and I looked at the average energy change was, where does that energy come from? Well, it is going to come from whatever apparatus does the unitary operation. Because in order to do a unitary operation, we need to turn on an interaction. And so we can ask, well, if the state of our system changes in energy, then clearly, because globally the energy is conserved, the apparatus will gain or lose energy. And the amount of increase of energy of the apparatus is exactly the negative of the gain of energy of the system. So it's the initial energy of the system minus the final energy of the system. And now I can consider, well, if I have a state rho, I can consider doing any unitary I like on it to try and maximize this quantity. That is going to be the ergodicity, which I've written here as epsilon rho. And a passive state rho has ergotropy 0. So passive state is exactly a state where I can do whatever unitary I want on it, but I can only increase its energy. I cannot actually take energy from it. Okay. So that's the notion of a passive state. And now discuss states that are not passive. So there are two kinds of states that are not passive. So if I write rho, if we write rho in the energy eigenbasis, then rho is not passive. First condition, there is an inversion. So rho has an inversion. And what is an inversion? An inversion is there's two energy levels, EM and EN, such that EM is greater than EN, and yet EM is greater than PM. So an inversion is basically the higher energy level has the greater population. Right? So we talked about this when we were discussing virtual temperatures. A negative virtual temperature means the higher energy level in a pair of levels actually has a greater population than the lower level. The other condition when rho is not passive is if rho has coherences, which, just to remind myself, EM is not equal to EN, and the rho MN is not equal to 0. So it has two energy levels that are not the same, and the off-diagonal element is not 0 between them. Okay. I'm going to quickly argue why these two statements mean that these two possibilities mean that rho is not passive. So in the first case, let's say rho has an inversion. So I have the condition there that I've written. So I'm not going to write a formal proof of this because this will be a tutorial question for you next week, but rather I give you a simple argument by taking a qubit. So imagine that I have a qubit. Remember, a qubit lies, actually, the qubit state I will just write this. If rho has an inversion, rho equals to something of the form 0, 0, and let's say P0, P1, P1 greater than P0. Then I simply do the unitary that flips these two things. So I simply do the unitary operation that will rotate P1 into P0 and vice versa. So this is a unitary around the x-axis, and then rho by unitary will go to P1, 0, 0, P0. This energy here is equal to P1 E of the system, because I take the energy of the ground state to be 0, the excited state to be just E of the system. But here E is equal to P0 E of the system, and so the ergotropy of rho is simply equal to P0 P1 minus P0. So this is rather straightforward. If I have an inversion, I simply swap the two states. And once I swap the two states, I gain energy because, of course, I've ended up pushing population from the excited to the ground state of the system, so that energy is going to come out somewhere. For the second case, when rho has coherences, for that I was going to use the box sphere. I'm going to try to just do this in the XZ plane because I'm not extremely adept at three-dimensional representations. But here we have the state 0, here we have the state 1, here the state plus, so this is Z, this is X. And now I've chosen this so that what I've done here is I've chosen it to be 0 and 1 without loss of generality for the energy eigenbasis to be the Z basis. So I'm calling the state 0 and 1. I'm labeling the energy eigenstate by 0 and 1. And so now we can ask the question, well, what is the energy of the state? And if I put a point somewhere here, let's say this is my rho, I can ask the question, well, what is all of the states that have the same energy as rho? What are the states that have greater energy as rho? And what are the states that have lower energy of rho? And because the energy of rho is basically equal to the population along Z and along 1, you get that the states that have the same energy are essentially those that pass through different color. The same energy rho. But then I can ask another question. I can say, well, if I do a unitary operation on that point, what are all the other states that I can go to? And this is something that I'll not prove here again, as I said, we'll do this in a tutorial. But the answer is that when you do a unitary operation on any state in the block sphere, you maintain the radius of the state in the block sphere, but you can go anywhere in the sphere otherwise. So for example, if you start on the surface of the block sphere, which is all of the pure states, you can use a unitary to go to any other pure state. As another example, if you start at the center of the block sphere, which is a maximally mixed state, you cannot use a unitary to go anywhere else. You're going to stay in the maximally mixed state, which is at the center. So the unitary orbit of rho is a circle, or actually a sphere, but I'm drawing a cross section because I'm in the XZ plane. This is the unitary orbit of rho. But now we see something very simple. As long as I start with a point that is off of the z-axis, which is basically a point with any off-diagonal element, because the only states that are incoherent are the ones that are along the z-axis, because they are mixtures of 0 and 1. Then if I start anywhere outside and I draw the circle, I'm always going to be able to move both up and down along the z-axis, because there's going to be a point which is closest to 0 and a point that is closest to 1, which means that I can always increase or decrease the state of rho by simply rotating from a point that has coherence to a point that is within the energy eigenbasis of the system. And so this is a simple argument to say that anything that has coherence, if I put any numbers here, then I can do the rotation to the energy eigenbasis, and by doing so, I can do the rotation one way or the other, and I will either get the maximum eigenvalue here or the maximum eigenvalue in the second spot. Maximum value is yes?
Sorry, what do you need to be off z-axis?
Well, if you are on the z-axis and you draw the unitary orbit, the point on the z-axis will be the extremum, because it will be a circle with the center being here. So if I started over, let's say I had my point, so if I started with a point actually here, then the circle, the unitary orbit would be this circle, which means that this is the extremum. Now, in this case, if I start here, this is the low energy state, so I can actually rotate and leave here. So this is the case of if I have an inversion. But if I start anywhere along the top line, which is this ray, yeah, if I have any point that starts up here, that is going to be the minimum of the circle. So yeah, it's even if I start on the z-axis but down, then of course I still have the inversion, so I can go. So the end result of this is that we know now that those two states, those two options are not passive. So the only possible passive states, which actually is the set of passive states that I will prove after I talk about linearization, are those that are there exists an energy basis, so they are diagonal in some energy eigenbasis ordered decreasing with respect to energy. And here is the populations. So the state has to be, I have to be able to find an energy eigenbasis such that it is diagonal in type 1 and it is ordered decreasing with respect to the populations. Now, the reason I said it has to be diagonal in some energy eigenbasis, because you might think from here, I've only talked about coherence between different energy eigenvalues, so why not have, dot diagonals between the states, is that you have to be kind of careful. And this is a little example. For example, to show you what can happen. So imagine that the Hamiltonian is the following. I have 4 states. This is energy 0, energy E, and energy, let's say 2E. Doesn't matter really what the energy is. Now I consider the first possibility I consider is that rho is equal to 1/3. So I call this now 0, 1, 2, and so on. 1/3, 1/3, 1/6, 1/6, and zeros everywhere else. This is clearly a passive state. I've just defined it as exactly diagonal in some energy eigenbasis and order decreasing with respect to energy. So clearly it's passive. But now imagine that I do the following thing. I keep the diagonal elements the same. Yes. Sorry, I will change the example very slightly because I made it little too. So I make this. Sorry, I expected to use the first 2 states. I ended up putting the degeneracy somewhere else. So let me make this even simpler. It's just a maximally mixed state of dimension 4. So it's 1/4 everywhere. But now the second example is I keep almost all of the orthogonal elements 0. So I keep a 0 in the first row and the 4th word column. But I also make this 1/4 and 1/4. So what I've done here is I've just put in some orthogonal element between the 2 states that are degenerate. So why is this a problem? The reason this is a problem is that I can use the same trick now about rotation to concentrate the population within the subspace. So this matrix here, 1/4, 1/4, 1/4, 1/4, this is actually just the density matrix of the plus state. And if the plus state in this 1 to eigenbasis, and I can do the same trick, I can rotate it so that all of the eigenvalues in 1. And so rho with the unitary will go to the following state: 1/4, 1/2, 0, and 1/2 with zeros everywhere else. And this is no longer passive because now you can see there are 2 inversions. This has the lower energy but it has a smaller eigenvalue. This has the lower energy than the other one, it has a smaller eigenvalue. So the thing about orthogonalism within degenerate subspaces is you're not going to be able to extract energy within that subspace. But it is possible that if you concentrate the eigenvalues, you might be able to extract energy with some other energy level. Which is why you have to be able to find some energy eigenbasis in which it's diagonal and order decreasing with respect to that. All right. Is there any question on this so far? Raise your hand. Majorization. What is majorization? Just to show of hands, how many in this lecture have already introduced to majorization in some form? Oh, that's a lot. Okay, almost all of you. Is this part of the QIT course? This part of the QIT course. Okay. All right. In any case, let me introduce it briefly. So, majorization is a relationship between vectors. So let me take any two vectors A and B, and R plus D. So majorization is actually defined without needing the plus, but we will always use the property vector, so we can just define this R plus D. And A is set to majorize B if and only if the sum from 1 to k, so any partial sum of the k largest elements of A is greater than the corresponding sum from 1 to k of the largest elements of B. So, as an example, this is an example I've used repeatedly. Let me take A to be 0, 2 over 3, 1 over 3, and B to be 1 over 3, 1 over 3, 1 over 3. So B is already, all the elements are equal, so B is already ordered in some sense. But because A is not ordered, we can also create an ordered version of A. And the ordering is greatest first, so the ordered version of A is 2 by 3, 1 by 3, and 0. And so now we can see the partial sums. So A1 is greater than B1 because A1 is 2 over 3 and B1 is 1 over 3. A1 plus A2 is equal to, this is the ordered version. A1 ordered is greater than B1 ordered. A1 ordered plus A2 ordered is 1, which is also greater than B1 ordered plus B2 ordered, which is 2 over 3. And the sum of all three, A3 ordered is equal to the same thing with B, which is equal to 1. And this is actually also the case because we deal with only property vectors. We will already also have that the full sum of all of the others is always going to be equal to 1 and equal to the other one. Okay, very important to emphasize. Majorization gives you an ordering between vectors, but it is a partial order because not every vector is comparable to another. So, as an example of two vectors are not comparable, take V1 is equal to 0.4, 0.4, 0.2, and V2, which is equal to 0.5, 0.25, 0.25. And you see, V2, these are already ordered and decreasing, so we don't have to order them again. V2 has the larger first element, but if I sum up the first two elements of V2, this is 3/4, 0.75. But if I sum up the first two elements of V1, it's 0.8, so it's larger. So one of the partial sums is larger in one case, but it's the opposite in the other partial sum. So these two elements are not comparable. So therefore, it is only a partial order. So, order. Okay. Why is majorization useful? We shall build up the usefulness of it now with a succession of statements. The first statement is if A majorizes B, then B is equal to D times A. D is a doubly stochastic transformation. What does this mean? This means that the sum over I of Pij, when written as a matrix transformation, is the same as the sum over J of Pij, which is equal to 1. So this is a matrix whose rows and columns both sum up to 1. Any row and any column. Okay. So if your image rise is B, you can always write B as a W stochastic transformation of A. This in turn is useful because of the following statement. This is due to, I don't know who it is due to, but it's called a work of von Neumann's theorem, which is that D itself is equal to sum over n Qn Gn, where Qn is probabilities. So, T and Tn permutations. So permutations are the simplest type of W stochastic transformations. You have a 1 in every row or column, a single 1 in every other element is 0. So what this says now is that every W stochastic transformation is really a convex combination of permutations, which is very useful because now you can also put this back into the transformation P is equal to dA. Yes?
There's a question online whether it should be larger or equal. Because the identity is a double stochastic transformation.
Yes, sorry, yes, you're right. Yeah, it's larger or equal to. So you can have A majorized B and B majorized A as well if, well, they have to then be, well, they are the same vector then, as their ordered vectors are the same, and they majorized B and B majorized A. They need not be the same vector, of course, because you can apply permutation, and the property of majorization doesn't change. Okay, and again. Okay, so right. So at the end we have a way to write any vector transformation that obeys a majorization relation in terms of permutations. Why is this useful? This is in turn useful because of the optimization of linear functions. So what is a linear function? A linear function is the following. If I have a function of a v1 plus b v2, and I can always write it for any constants a, b, and vectors v1 and v2 as a of f of v1 plus b f of v2, and this implies that f is linear. So remember that this is to be true for all A, B in R and B1, B2 in So that is a linear function. And now what I can consider is, imagine now I did a transformation where I took, so B2 is equal to, let's call it B prime. The transform state is equal to some doubly stochastic matrix B, right? So, which is the same as saying that B prime is majorized by B. Okay, but now what I want to consider is, I want to look at the value of a function, a linear function f on B prime, and I want to consider trying to maximize or minimize, getting the extreme values of this function. So I ask the question, what is the extremum, which is overall on P, what are, because extremum can be minimum or maximum of f of B prime. Okay. And so now I use the fact that it's a linear function. I do it in a number of steps. So I say f of B prime is f of d b, which in turn is f of sum over n qn of pn times d. But because it's a linear function, I can take it inside the bracket. So I'm going to end up with sum over n qn of the function acting on the permutation of b. Okay, but this is now a convex combination because qn is a probability vector. It's a combination of all of these, which means that the minimum of f of pn b overall n is going to be less than the value of this f of b prime, whatever it is, which is going to be less than the maximum of f of pn b overall n. And so now this gives us a very neat answer to the question, if I do a general doubly stochastic transformation on B with the goal of making some linear function maximum or minimum, then what is the doubly stochastic transformation? All I have to do is look among all the permutations. And I guarantee that one of the permutations will have maximum or minimum value. It can be that many permutations satisfy this property, that many permutations give you the same value to the maximum. And in that case, any convex combination of the permutations is also going to do so, but at the very least, we guarantee that the permutation does. Okay. So, as a very simple example, we can imagine that the A and B that we had there, you can consider them to be qubit states. So they are just the populations of some qubit. And I'm going to take F to be the Hamiltonian corresponding to those. So if I can write f as a linear function, it also means that I can write f of b as the sum over I fi vi. It's a linear function. I can write it as a scalar product, some scalar product on that vector. So take as an example, f is equal to the following 0, e, and 3e. So I've just given it three values, and E is really acting like an energy now. So I'm making this a ground state energy, excited state of 3. And so then I have, well, I have now A. So I want to know what is f of d of A and the max and the minimum value of this. And I already know I have to just search for the permutation that will give us the maximum minimum value. And this is something we can do intuitively. We know that the energy is increasing first, second, and third element. So of course, if we want to have the maximum amount of energy, we just put the maximum population in the third element. So this, the maximum will be f of the following vector, 0, 1 over 3, 2 over 3. So I just have to pick that permutation. And the minimum will be the opposite. I put as much as I can in the ground state, then the next, and then the last. So I've not written the permutations down explicitly, but you can see the first one is just swap the second and third element, and then the second one is I guess a three cycle between all three. Is there any question? Yes? So what I've used is the fact that the expression that I have for f of b here, this is a convex combination of the P and D, the set of the P and, oh sorry, not P and D, but rather the set of the F of P and D. So because the convex combination of it, it means it will lie, basically I list all of those values and it will lie in the range of those values. Yes? Yes, indeed, yeah, yes, sorry, it is both ways. I wrote it there because I needed that way then, but indeed, that is, yeah, exactly the identical conditions. If A majorizes B, then B is B times A. Yes, thank you. That was
Sorry, what was the statement?
The statement was the majorization and the doubly stochastic statements are if and only if. So if A majorizes B if and only if B can be written as a doubly stochastic transformation. Now I have 10 minutes for the sure horn theorem. No need to quantum. So the usefulness of, I'm going to keep this there. The usefulness of this majorization is that it sort of gives us something that is maintained when we do transformations. So it's not like when we transform a vector, we just completely lose any sense of its properties. We know that with respect to the initial one, it is always going to have, well, the final list of vector elements is always going to be majorized. And this is something now that also translates to quantum mechanics. I have a very useful theorem labeled on theorem. Now, the statement of the theorem is essentially the following. We will really want to use a corollary of the theorem, but I'll give you what the theorem is first. So if H and lambda belonging to R plus D are such that H is majorized by lambda. So I give you two vectors, property vectors, such that H is majorized by lambda, then there exists a Hermitian matrix capital H. This is the first time I am now using H for something else. I realize that I'm using the same notation. I think I'm using the same notation if you decided to look it up in Wikipedia. But such that H is equal to the diagonal elements of this Hermitian matrix, and lambda is equal to eigenvalues of this Hermitian matrix. So if I give you two property vectors, one of which is majorized by the other, I can always use the majorized one as a diagonal of a Hermitian matrix whose eigenvalues are the majorizing vector. This is the statement of Schur law. Now, the corollary that is of particular importance to us is that the eigenvalues of rho always majorize the diagonal elements of rho. So this is a corollary, and I'm going to prove this corollary. This is a Schur theorem. It's full generality. I'm not going to prove the theorem, but I'm going to show you how the corollary works. This is particularly simple. So imagine now that I have so take a take some row, state. Actually, it doesn't have to be, because it does not have to be a state, I can just take it to be some matrix H. This is commission. Now, because it's a mission matrix, we know that we can diagonalize this. What that means is there exists some unitary U such that H is equal to U, W, U inverse, where this is diagonal, and this is unitary. Okay, so we know that this exists from linear algebra. Every Hermitian matrix can be diagonalized. I can write some unitary, some diagonal. Now let me write this whole thing as a matrix multiplication. And in particular, what I want to do is I want to look at the diagonal elements of this H. So I write, what is the diagonal element of this H? This is going to be some HII. What is that equal to? Now I just use matrix multiplication. This is going to be, I'm going to have to take UIK, WKK, U inverse or dagger, KJ. We're going to sum over K. Now remember that W is a diagonal element, so all other elements that are not of the form KK are already 0. This is why this simplifies with only a single sum. There's only a sum over K. Okay. Check.
Did you mean HIJ on the left?
Oh, sorry. Sorry, I didn't know this is what HII. So I actually don't know. Thank you. Yes. If I did HIJ, then that would be the general one, but I don't need that. I just need this here. Do that. Yeah. Very good. Yes. So now is. So this is equal to the sum of. We know that
if you use the transfer, should be hyphen.
No, so this is because it's U, W, U dagger, and the elements, so it's, say, H is equal to A, B, C, then H, I is A, I, K, B, K, K, C, K, I. So whatever C is.
I thought it was U, W, U minus 1.
U inverse is U dagger. These are the same. So I just changed from U to U dagger. I mean, it's the same, yeah. Okay, so now I use the fact that U dagger KI is I can now switch the indices because this is really a transpose. So this is going to be UIK mod squared because this here is the same as UIK star, the complex conjugate of VKI. And so I have UIK mod squared times WKK. Yep. Okay, so UIK mod squared. And now this is actually a doubly stochastic matrix because if I look at UIK mod squared as a matrix, so I can now define D IK is equal to UIK mod squared. So then it follows that the sum over I or over K of DIK, which is equal to the sum over I or K of UIK mod squared, is equal to 1 because U is a unitary matrix, and one of the properties of the unitary matrix is that all of its rows and columns are orthonormal vectors. And so what we have proven here now is that HII as a vector is majorized by the same W as a vector. Or I mean, this is the vector I can use. Okay. So what I've just shown is that any Hermitian matrix, and this includes, of course, quantum states, has the property that its eigenvalues majorize its diagonal elements. And the last thing I will say to conclude this lecture is the reason this is important is because for most of our course, and actually all of thermodynamics, the unitary operation is the major operation we consider. And the unitary operation has the advantage that it preserves the eigenvalues of the state. And so what this theorem gives us is it gives us some control. We can do as many unitary operations as we like, but we will always have the eigenvalue vector remains the same. So however the diagonal elements can change, we know one constraint to their change. We know that whatever the diagonal elements are, they will always remain majorized by the vector of eigenvalues, and that is something that does not change with the unitary operation. All right. So I will conclude this lecture here. In the next lecture, we will take this to continue the story about passivity and to prove somehow that the only states that are well and truly passive, even under composition, are the thermal state. We will continue the lecture by doing two other ways of understanding why the thermal state is somehow so special. One, because it's completely passive. One, because it's the state of least information. And the third will be of equilibration. Thank you.